Good morning. This is an audio recording for visually impaired students. Today I am going to read a chapter named Arenes and Aromaticity from Organic Chemistry, written by Dr. S.N. Dhawan. In the earlier stage of development of organic chemistry, a large number of organic compounds were obtained from natural sources such as essential oil, resins, which had one property in common, a pleasant odor. It is due to this reason that these compounds were termed aromaticity, Greek aroma, fragrant odor. The term aromatic is, however, a misnomer since it is now known that all aromatic compounds does not necessarily possess pleasant odor. Besides, there are several aliphatic compounds such as anyl acetate which too have fragrant smell. Further analysis of aromatic compound revealed that they had a higher percentage of carbon than the corresponding aliphatic compound and possessed a ring of 6 carbon atom having 3 conjugated double bond. For example, they all contain a benzene ring. All of them are cyclic compound but have property quite different from those of acyclic compound which resemble aliphatic compound. The term aromatic now refer to benzene and all those compounds which resemble benzene in chemical behavior. Aromatic compounds are further divided into two categories, benzoate and non-benzoate. Aromatic compound depending upon whether they contain a benzene ring in them or not. Benzoate compound. Aromatic compound containing one or more benzene ring in their molecules are called benzoate compound or simply benzoates. For example, benzene, toluene, chlorobenzene, phenol, naphthalene, anthracene, etc. Non-benzoate compound, aromatic compound which do not contain a benzene ring in their molecules are called non-benzoate compound. For example, cycloheptatrienyl cation, azulene, triponolane, ferroquine, etc. Nomenclature of benzene derivatives. The parent aromatic compound C6H6 is named as benzene in the common as well as in IUPAC system. Derivative of benzene are named as substituent benzene. The following rules are generally followed. A. Monosubstituted benzene derivatives. The name of monosubstituted benzene derivatives is obtained by prefixing the name of substituent to the word root benzene, for example, bromobenzene, nitrobenzene, ethylbenzene, and isopropylbenzene. In some cases, the name of the substituent is written after the word root benzene. For example, benzene with N2Cl called benzene diazonium chloride, benzene with SO3H named benzene sulfonic acid. Second, a number of mono-substituted benzene derivatives have, however, special name. For example, benzene with NH2 name aniline, benzene with OH name phenol, benzene with OCH3 name anisole, benzene with CHO called benzyl aldehyde, benzene with COH called benzoic acid, benzene with CN called benzonitrile, benzene with CH3 named toluene, and benzene with CH double bond CH2 gives styrene. Di-substituted benzene derivatives. In case of di-substituted benzene derivatives having two similar atom or group, the prefix di is added before the name of the group and the relative position of two groups are indicated by the symbol O ortho for 1 and 2, M meta for 1 and 3, and P para for 1 and 4 position respectively. Usually in the common system, these symbols are used, but in IUPAC system, Arabic numerals are preferred. For example, bromine present at 2 bromo position, then it is known to be common name ortho dibromobenzene and IUPAC name 1,2-dibromobenzene. Same nitro compound present at 2 meta position, then it is known to be the common name 3-di nitrobenzene and name 1,3-di-nitrobenzene. Third, chlorine present at para position, then it is known to be p-dichlorobenzene or 1,4-dichlorobenzene. When a disubstituted benzene derivative contains two different functional groups, it is named as the derivative of the compound with the principal functional group at position I. For example, benzene ring with COOH or NO2. Name 4-nitrobenzoic acid. Benzene OH NH2. 2 ammonium phenol. Benzene with CN and COCH3. Then its name is 3,1 oxyl ethyl benzonitrile. If both the functional group present in the benzene ring are substituted functional group, then they are arranged in alphabetic order. C. Polysubstituted benzene derivative. If one of the substituent give a special name to the monosubstitute benzene derivative, then the numbering of the ring carbon atom begin with that substituent and the compound is named as the derivative of that molecule. For example, benzene with OHCH3 name 4-iodo-2-methyl-phenol. Benzene with COH Br, then its name is 2,4-dibromobenzoic acid. Benzene with 3 bromine and 1 aniline, then its name is 2,4,6-tribromoaniline. Benzene with 3 nitro and 1 CH3 group, then its name is 2,4,6-trinitrotoluene. Third, if a tri-substituted benzene derivative contains three different functional groups, it is named as a derivative of the compound with the principal functional group at position I. For example, benzene ring with CO2H bromine OH, then its name is 3-bromo-4-hydroxybenzoic acid. Benzene ring with CHO OCH3OH, then its name is 4-hydroxy-3-methoxybenzylaldehyde. If all the functional group present in benzene ring are such which are normally treated as substituent groups, the various groups are arranged in alphabetic order with the group name first in the alphabetic order getting the lowest locant provided it does not volatile the lowest locant rule for all substituent. For example, benzene with 1 chlorine 2 nitro called 1 chloro 2,4 dinitrobenzene. Benzene with one bromine and two chloro, then its name 1 bromo 3,5 dichlorobenzene, and bromine with 1 CH2CH3 group, 1 nitro group, and 1 fluorine, then its name is 4 ethyl 1 fluoro 2 nitrobenzene. Benzene nucleus and side chain. The ring of 6 carbon atom present in benzene and its derivative is called the nucleus. An alkyl group or an other group contain at least one carbon atom attached to the ring is called the side chain. For example, nucleus plus side chain. Benzene with CH2Cl. Benzene is a nucleus and CH2Cl is a side chain. It may be noted out here. The group like OH, NH2, Br, SO3H, etc. can be termed as side chain as they do not contain any carbon atom. Compound in which the functional group is linked to the benzene ring are called the nuclear or a ring derivative, and those in which it is present in the side chain are termed as side chain derivative. Aryl group. Group contained by removal of one or more hydrogen atom of benzene or its derivative are called the aryl groups. Some important aryl groups along with their name are given below. One hydrogen removed called phenyl. Two benzene ring with CH2 remove one hydrogen called benzyl. Same compound toluene with removal of two hydrogen called benzyl. Same compound with the removal of three hydrogen called benzo. And have toluene, but one hydrogen is removed from ortho position, and it's called O-toluene. In the same case, the new aryl groups will be formed. It may be mentioned here that the phenyl group may also be present be any one of the following symbol: C6H6 dash O dash or phenyl dash. Structure of benzene. From elemental analysis and the molecular weight determination, the molecular formula of benzene has been found to be C6H6. This formula implies that benzene has 8 hydrogen atoms less than the corresponding saturated alkene C6H14 hexane. Thus, benzene should be highly unsaturated compound. This is supported by the following two observations. First, benzene add 3 molecules of hydrogen in presence of running nickel or platinum as catalyst at 473 5 to 23 Kelvin to form cyclohexane. On treatment with both ozone, benzene form are triozonide. Benzene react with O3, then it will give triozonide. Third, in the presence of sunlight or in absence of halogen carrier, benzene add with 3 molecules of chlorine to form benzene hexachloride. In spite of the presence of 3 double bond, benzene behave like a saturated compound as spotted by the following two effects. First, benzene undergo the substitution rather than the addition reaction. Although benzene is expected to be highly unsaturated, yet it does not go addition reaction so typical of unsaturated hydrocarbon such as alkene and alkyne. For example, it does not decolorize brown in carbon tetrachloride solution. Instead, it undergo substitution reaction, nitration, sulfonation, halogenation, Friedel-Crafts reaction, which are characteristics of saturated compound. For example, when treated with bromine in presence of trace of FeBr3, benzene from bromobenzene. Benzene react with Br2 in the presence of FeBr3, then it will give C6H5Br plus HBr. But when it reacts with bromine plus CCl4, then it does not show any reaction. That's why it doesn't show any addition reaction. Similarly, halogen acid do not add to benzene. Second, benzene is resistant to oxidation. Unlike alkene and alkyne, benzene is resistant to oxidation and remain unaffected even on treatment with powerful oxidizing agent such as chromic acid, potassium permanganate, etc. Thus, benzene resists oxidation like saturated compound. Calcule structure. The first insight into the structure of benzene was given by Friedrich August Kajal. He proposed that the six carbon atoms of benzene are joined to each other by alternate single and double bond to form hexagonal ring shown in figure 7.1. Each carbon is further connected to the hydrogen atom. Objection to Kajal structures. There are three objections to Kajal structure. First, Kajal structure would predicted only one monosubstituent product and two ortho disubstituent product A and B shown in figure 7.2. In structure A, there is a double bond between two carbon atom carrying chlorine atom, but in structure B, there is a single bond. If Kajal structure were correct, both these isomers should exist and should have different property. But only one orthodichlorobenzene is known. To account for this, Kajal proposed a dynamic equilibrium between the two structures shown in figure 7.3. In other words, position of single and double bond are not fixed but oscillate back and forth between adjacent position. Stability. Why is it that benzene show remarkable stability towards oxidizing agent like KMnO4 and undergo substitution reaction even though it contains three double bond? Second, equivalency of carbon bond length. Kegel formula for benzene contain two kind of bond, single and double bond. But X-ray diffraction studies have shown that the structure of benzene in a regular hexagon with an angle 120 degree and all carbon-carbon bond length are equal 1.39 angstrom or 139 picometer, which lie in between carbon-carbon single bond length of 1.54 angstrom or 154 picometer and double bond of 1.34 angstrom or 134 picometer. Thus, Kajal structure failed to account for the unusual stability of benzene and the equivalency of all carbon-carbon bond length in benzene. To account for this objection, the following other alternative structure were proposed for benzene from time to time by different scientists, but all these were rejected on one ground or the other. Resonance structure. To account for the above limitation of Kajal structure, it has been suggested on the basis of quantum theory that benzene is a resonance hybrid of the two Kajal first and second and three diverse structure third and fourth. Calculation have further revealed that the two Kajal structure differ only in the arrangement of electron, make major contribution toward resonance. Thus, two Kajal structure first and second may be regarded as canonical form of benzene. The actual structure of benzene is neither represented by one nor by second, but is a resonance hybrid of these two structures. Further, since these two canonical forms are of equal energy, so they contribute equally 50% toward the resonance hybrid. In other words, structure of resonance hybrid is in between these two Kajal structure. This means that any two adjacent carbon atom of benzene molecule are neither joined by a pure single bond nor by a double bond. As a result, all the carbon-carbon bond length are equal. For example, 1.39 angstrom or 139 picometer and lie in between. C double bond C bond length of 1.34 angstrom or 134 picometer and carbon single bond length of 1.54 angstrom. 154 picometer. The resonance hybrid or the actual molecule of benzene is usually represented by the formula A. Further, a resonance hybrid is always more stable than any of its canonical structure. Thus, the actual molecule of benzene is more stable than either of the two canonical structure. The magnitude of stability conferred on a molecule as a result of resonance is expressed in a term of resonance energy or delocalization energy. It is defined as the difference in internal energy of the resonance hybrid and that of the most stable canonical form in case of benzene. This resonance energy has been determined to be 150 to 60 kilojoule, 36.0 kilocalorie per mole. Calculation of resonance energy. The resonance energy of benzene can be calculated from heat of hydrogenation data. Heat of hydrogenation is the amount of heat evolved when 1 mole of unsaturated compound is hydrogenated in the presence of catalyst. When benzene is fully hydrogenated, it gives cyclohexane and 208.36 kilojoule or 49.8 kilocalorie per mole of heat is evolved. On the other hand, cyclohexane having a 6-membered ring and one double bond when hydrogenated gives cyclohexane and 119.66 kilojoule 28.6 kilocalorie per mole of heat is evolved. If the three double bond of benzene did not interact or if these were there were no resonance as would be the case in the hypothetical cyclohexatriene molecule with the three non-interacting double bond in a six-membered ring, then three times the heat of hydrogenation of cyclohexene. For example, 119.66 multiplied 3 give 358.98 kilojoule or 85.8 kilocalorie per mole would be evolved. Cyclohexene plus H2 catalyst, then it will give cyclohexane and give minus 119.66 kilojoule per mole. Cyclohexatriene hydrogenated to give cyclohexane and it will give energy minus 358.98 kilojoule per mole. Benzene get hydrogenated, give cyclohexane and release energy minus 208.36 kilojoule per mole. The actual molecule of benzene is 358.98 minus 208.36 give 150.62 kilojoule or 36 kilocalorie per mole, more stable than the hypothetical cyclohexatriene molecule. In other words, 150.62 kilojoule or 36 kilocalorie more is a resonance energy of benzene. Molecular orbital structure of benzene. According to MO theory, all the carbon atom of benzene are assumed to be sp2 hybridized. Each carbon atom forms two carbon-carbon sigma bond with the neighboring carbon atom and one CH sigma bond with the hydrogen atom. Thus, in all, there are 6 C sigma bond and 6 CH sigma bond which all lie in a one plane, and the angle between two adjacent sigma bond is 120 degree. Each carbon is now left with an unhybrid p orbital. These six unhybridized p orbitals have one electron each and are not only one parallel to each other but are also perpendicular to the plane of sigma bonded carbon skeleton. Further, any two p orbital on adjacent carbon atom are close enough for a sideway overlap to form pi bond. Now there are two equally good ways in which p orbital on adjacent carbon atom can overlap to form three sigma pi bond are shown in figure 7.5a and 7.5b. In fact, each 2p orbital equally overlap equally well with 2p orbital on adjacent carbon atom on either side to form two donut shaped pi electron, one of which lie above and other below the plane of carbon and hydrogen atom as shown in figure 7.6. Further, according to MO theory, when 6 2pz orbital, each containing one electron, combine 6 molecular orbital, resulting out of which 3 psi1, psi2, psi3 are bonding, while the remaining 3 psi4, psi5, psi6 are anti-bonding. The bonding MO psi1 encompasses all the 6 carbon atoms. It does not have a node and hence is of lowest energy. The next two MO psi2 and psi3 have one node each and thus are degenerating, are of equal energy. Since the energy of any MO depend upon the number of node it has, therefore MO psi2 and psi3 with one node each are of high energy than MO psi1 which does not have any node. In accordance with Pauli exclusive principle, each of these three bonding MO contain a pair of electrons in the ground state of benzene molecule. However, when the benzene molecule is in the excited state, one or more pi electron will occupy the higher energy antibonding molecular orbital. Although Psi2 and Psi3 MO are of two different shape, yet like Psi1 they provide equal electron density at all. The 6 carbon atom. The net result is that these three bonding MO combine together to give two continuous donut shaped electron cloud. One line above and other below the plane of the carbon atom and shown in figure 7.6. From the above discussion, it is evident that 6 pi electrons are not confined to three distinct double bonds as shown in Kajal structure first and second, but occupy three bonding MO and are delocalized over the entire conjugated system. In other words, each pair of pi electron is involved in the formation of several bonds. This participation of pi bond in the formation of more than one bond is called delocalization of an electron, and it is this delocalization of an electron which makes the molecule more stable. Representation of benzene structure. Due to delocalization of pi bond, benzene is now represented as the regular hexagon with a circle in center. However, the conventionally calculus structure is still been widely used, and we shall be use both these representation in this book. Whereas the hexagon represent the 6 carbon atom, the circle represents 6 complete delocalization pi electron. It may be not here that it is this delocalization of pi electron which makes benzene more stable than the hypothetical cyclohexatriene molecule Kajal structure. Aromaticity. The most significant feature of benzene and its derivative is that they are more stable than the corresponding acyclic polines and possesses large resonance energy. Such compound which possess large resonance energy are called aromatic compound, and then extra stability of such compound is referred to the special property called aromatic character called aromaticity. Since benzene is a cyclic conjugated polyene, therefore it was thought that its lower cyclobutadiene and higher cyclooctatetraene Vinolages should also exhibit aromaticity. Later on, these compounds were actually prepared, and it was found that whereas cyclobutadiene is highly unstable and cyclooctatetraene is stable, thought not as stable as benzene. Instead, it behaved like an ordinary polyene with isolated double bond. Thus, aromaticity is simply not related to cyclic conjugated polyenes, but is related to some magic number of pi electron in planar monocyclic conjugated polyenes. Huckel rule. On the basis of molecular orbital calculation, Erich Huckel, a German physicist in 1930, pointed out that in order to be aromatic, a compound must fill the following criteria. First, the molecule or ion must be flat or planar or nearly so. Second, it should have cyclic cloud of delocalized pi electron above and below the plane of the molecule. Third, the pi electron cloud should encompass all the carbon atom of the cyclic system. Fourth, the total number of pi electron in the molecular species or ion should be 4n plus 2 pi, where n is equal to 0, 1, 2, 3, etc. These criteria are collectively known as 4n plus 2 pi electron or simply Huckel rule, which may be stated as monocyclic planar completely conjugated polyenes containing 4n plus 2 pi electron and having a single cyclic pi electron cloud encompassing all the carbon atom in a ring are aromatic in nature. A molecule which does not satisfy any one or more of the above conditions is said to be non-aromatic. Theoretical base of the Huckel rule. According to quantum mechanical concentration, an aromatic system possesses a closed shell of pi electron corresponding to inert gas configuration. Huckel point out that energy of MOs of aromatic system have a very simple characteristics pattern in which there is always one orbital of lowest energy followed by degenerate pair of orbital having the same energy in order of increasing energy. However, in case of polyenes containing even number of carbon atom, there is an additional antibonding orbital of highest energy. Filling of electron in these orbitals take place in following manner. First of all, two electrons are filled in the lowest energy MO, then remaining electrons are placed in degenerate pair of orbitals strictly in according with Huckel-Hund rule. Thus, if conjugated planar monocyclic system has 2, 6, 8, 18, etc. pi electrons, the lowest energy MO and all other degenerating pair of molecular orbital would be occupied by 2 electrons each. Because of these closed shell filling of orbitals, such systems are quite stable and hence are aromatic. On the other hand, if a monocyclic planar conjugated system has 4, 8, 12, etc. pi electron, there will be always two singly occupied degenerating orbital. Because of this arrangement of electrons, such systems are highly unstable and are called anti-aromatic. For example, square planar cyclobutadiene with 4 pi electron in anti-aromatic. Similarly, planar cyclooctatetraene with 8 pi electron will have two singly occupied degenerating orbital and hence it should be anti-aromatic. From the above discussion, it followed that the energy of 4n pi electron system is higher than the hypothetical structure having independent double bond in which p orbital do not overlap and hence there is no delocalization. In other words, the system are destabilized by resonance. Application of Huckel rule. In the light of Huckel rule, it is evident that aromatic compound need not necessarily contain a benzene ring All what is required is that the molecule of the compound must be planar and should contain cyclic cloud of delocalized 4n plus 2 pi electron above and below the plane of the ring. The cyclic conjugated planar molecule contain 2 n is equal to 0, 6 n is equal to 1, 10 n is equal to 2, 14 n is equal to 3 pi electron should be aromatic. Although these rules were originally derivative from monocyclic carbocyclic containing only carbon and hydrogen atom system, they are applicable to other system as well as. Let us now test the validity of this rule. First, 2 pi electron system. The simplest 2 pi electron system is cyclopropene, but 2 pi electrons are not completely delocalized over all the 3 carbon atom. Therefore, cyclopropene is not aromatic. On the other hand, in cyclopropenyl cation, the 2 pi electrons are completely delocalized. In the light of Huckel rule, it should be aromatic. This has actually been found to be so. In fact, cyclopropenyl cation is quite stable, and the salt of the number of cyclopropenyl cations, such as triphenyl cyclopropenyl cation, have actually been isolated and stored in bottle. Other example of aromatic 2 pi electron system are 1,2-diphenyl cyclopropyl cation, 1,2-di and propyl cyclopropynyl cation, 1,2-di and propyl cycloprop 2 in 1 on 1,2,3,4 tetraphenyl cyclobutadienyl cation. Second, 6 pi electron system. Benzene is a perfect example of an aromatic compound containing a planar hexagonal system of 6 pi electron. Cyclopentadiene, on the other hand, contains 4 pi electron and hence it is not aromatic. However, cyclopentadienyl anion is aromatic since it contains delocalized 6 pi electron and is also a planar. Cycloheptatriene also contains 6 pi electron, but the electrons are not delocalized over 6 carbon atom and not over all the 7 carbon atom of the ring. Furthermore, it is not planar, therefore it is not aromatic but behave like a typical polyene undergoing electrophilic addition reaction. Cycloheptatrienyl cation. Propylium ion, on the other hand, is planar and also have 6 pi electron, which are completely delocalized over the entire cyclic system and hence is aromatic. Further examples are provided by tropolone, and ferrocene. In tropon, due to the displacement of electron toward the more electronegative oxygen atom, the seven-membered ring become aromatic due to suicide of electron, and as a result of this dipolar structure, it has high dipole moment of 4.17 dBi. Similarly, we can explain the aromaticity of tropolone. In azulene, due to transfer of electron, each ring get aromatic succeed and hence azulene is aromatic nature. Similarly, ferrone owns its stability to the aromatic succeed. Third, system with 10, 14, 18 electron. They are discussed under aniline in section 7.8. Fourth, heterocyclic compound. The heterocyclic compounds such as pyridine, furan, thiophenone, pyrroline, etc. all are aromatic since they contain a cyclic system of 6 pi electron which are completely delocalized. Whereas in pyridine, the heteroatom contribute 1 pi electron. In furane, thiophene, and proline, each heteroatom contribute 2 pi electron toward the aromatic system. Fifth, polycyclic compound. Huckel will also explain the aromatic character of some polycyclic compound. For example, naphthalene, which contain 10 pi electron, N is equal to 2. Anthracene and phenolphthalein each contain 4 pi electron, N is equal to 3. All are aromatic. Pyrene contains 6 pi electron, but it behaves like an aromatic compound. Therefore, it is suggested that only the peripheral electron contribute toward forming a closed loop of 4 pi electron, while the 2 pi electron of the internal C13, 15 and 16 double bonded do not. This suggestion is confirmed by the fact that when this double bond is replaced by 2 methyl substituent, the resulting 15-16 dihydrodimethyl binanes still show aromatic character. Aromatic, anti-aromatic and non-aromatic compound. We have discussed above that planar cyclic conjugated polyene which have 4n plus 2 pi electron delocalized all over the carbon atom offering are aromatic in nature. This delocalization leads to stability. The extent of this stability is measured in terms of delocalization energy dE. There were two methods to calculate the delocalization energy of cyclic conjugated polyene. First, Huckel molecular orbital and second, perturbation molecular orbital method. First, according to HMO method, delocalization energy is expressed as a difference in pi energy of a cyclic conjugated polyene in which pi electrons are completely localized and the corresponding hypothetically cyclic polyene in which the pi electrons are localized. For example, the dE of benzene is determined by calculating the difference in pi energy of the real benzene molecule in which pi electrons are completely delocalized and hence the hypothetical 135 cyclohexatriene Kajal structure in which pi electrons are localized in three distinct pi bonds. Second, the second method of calculating the delocalization energy was given by M.J.S. Devar. This method is based upon the perturbation molecular orbital theory. According to PMO method, delocalization energy is defined as the difference in the pi energy of the cyclic conjugated polyene and an acyclic conjugated polyene having the same number of double bonds. In this method, the cyclic conjugated polyene is considered to be derivative from the corresponding acyclic conjugated polyene by just removing one H atom from each end of the chain and then joining the two ends together. Depending upon the magnitude of the delocalization energy, cyclic conjugated polyene have been divided into three types. First, a cyclic conjugated polyene is said to be aromatic if it has large delocalization energy relative to cyclic anole. For example, 135 hexatriene contains 6 pi electron, lose 2 electron and give benzene 6 pi electron, D greater than that of 135 hexatriene aromatic. Alkyl contain 2 pi electron, loses 2 electron, gives cycloprophenyl cation. 2p electron D is greater than that of the alkyl cation aromatic. Second, a cyclic conjugated polyene is said to be anti-aromatic if its delocalization energy is lower than the corresponding conjugated cyclic polyene. For example, 1,3-butadiene loses 2 electron form cyclobutadiene. 4 pi electron D is lower than of 1,3-butadiene anti-aromatic. Third, a cyclic conjugated polyene is said to be non-aromatic if its delocalization energy is comparable to that of the corresponding acyclic conjugated polyene. 1357 octatriene give cyclotetratriene. 8 pi electron De is same as that of 1357 octatriene non-aromatic. It may be noted out here that the term D is a measure of the stability of cyclic conjugated polyene relative to the corresponding cyclic or acyclic conjugated polyene. As such, it has nothing to do with the chemical reactivity and the thermodynamic stability of the molecule, which is measured in terms of resonance energy. Thus, a molecule may have a large delocalization energy but may still be reactive. Let us now discuss in some detail the some concept of anti-aromatic and non-aromatic. We have discussed about that the planar cyclic conjugated polyene contain 4n plus 2 pi electrons are stabilized by delocalization of pi electron relative to the corresponding cyclic or acyclic conjugated polines and hence are aromatic. The stability of this compound is due to the fact that all their bonding M are completely filled in a ground state. But delocalization of pi electron does not always leads to stabilize. In fact, HMO and PMO calculation have shown that in planar cyclic conjugated polyns contain 4 n pi electron. Delocalization even leads to destability. Such planar cyclic conjugated pollen containing 4 n pi electron, which are destabilized by delocalization, are called anti-aromatic compound, and the phenomenon is known to be an anti-aromaticity. Consider, for example, cycloprophenylamine. It can be represented as a resonance hybrid of three canonical structure, second and fourth. HMR calculation have shown that the resonance hybrid first is of the higher energy than any of the canonical structures second, third, fourth, and hence cycloprophenylamine is anti-aromatic. In a similar way, cyclopentadienyl cation fifth can be represented as a resonance hybrid of five canonical structure, 6th to 10th, but still the cation is of higher energy. Thus, like cyclopropylamine, cyclopentadienyl cation is also anti-aromatic. Perhaps the most truly investigated anti-aromatic compound is cyclobutadiene. It is such that an unstable molecule that even at 195 Kelvin it undergo aldyl Haldar cycloaddition to form dimer. Cyclobutadiene react at 195 Kelvin gives cyclobutadiene dimer. The high reactivity of cyclobutadiene is not merely due to angle strain, since cyclopropene derivative in which the strain is expected to be even more are non-compound. The reactivity is probably due to anti-aromatic. From the above discussion, it follows that the possibility of existence of many resonance structure of any compound or its ion does not necessarily mean that the compound or ion should be unusual stable and hence aromatic. The number of pi electron is the main criteria for stability or instability. According to HMO calculation, planar completely conjugated pollens contain 4 n pi electron are destabilized relative to their corresponding cyclic analogy with localized pi bonds and hence are anti-aromatic. The instability of this compound is due to reason that two of their electrons are present either in non-bonding or anti-bonding molecular orbital in the ground state of the molecule. Non-aromatic compound. If the stability of cyclic conjugated pollen is comparable to the corresponding cyclic or acyclic pollen with localized bond, the cyclic compound or ion is said to be non-aromatic and the phenomenon is called non-aromaticity. We have discussed above that planar cyclic conjugated pollen contain 4 and pi electron are destabilized by delocalization and hence are anti-aromatic. If, however, the structure of molecule is such that it can assume a non-planar geometry, the delocalization of pi electron is prevented and destabilization is avoided. In such cases, the cyclic conjugated and the corresponding cyclic or acyclic conjugated pollen with localized bond have comparable stability and hence are non-aromatic. For example, planar cyclooctatetraene is expected to be anti-aromatic. But if we know that a regular octahedron have a bond angle of 135 degree while sp2 bond angle are 120. Therefore, in order to avoid this large angle strain, the molecule assume a non-planar shape like tube shape. Since cyclooctatetraene is not planar, it is neither aromatic nor anti-aromatic, but it is non-aromatic. This is due to reason that in the tube-shaped geometry, all the p orbital are no longer parallel and hence destabilization due to delocalization is prevented. As a result, 8 pi electrons are localized in 4 distinct pi bonds. In other words, it behaves as a typical alkene and undergo electrophilic addition, Br2HCl, etc., and oxidation reaction KMnO4O3, etc. Similarly, planar cycloheptatetraenyl anion is supposed to be antiaromatic, but in reality, like cyclooctatetraene, it has non-planar geometry. As a result, destabilization is avoided and hence it behaves as a non-aromatic compound. Anilines. Completely conjugated monocyclic polyene contain an even number of carbon atoms are called aniline. They have the general formula CH double bond CHN, where N is equal to 2, 3, 4, etc. They are named by indicating the name of carbon atom in the ring enclosed in square bracket before the root word aniline. The cyclobutadiene N is equal to 2 can be regarded as a 4 aniline. Similarly, benzene N is equal to 3, cyclooctatetraene N is equal to 4, can be called as 6 aniline, 8 aniline, respectively. Aromatic, antiaromatic, and non-aromatic character I discussed above. Aniline may be aromatic, antiaromatic, or non-aromatic. For example, 4-aniline cyclobutadiene is antiaromatic, 6-aniline benzene is aromatic, and but 8-aniline like cyclooctatetraene is neither aromatic nor antiaromatic but is non-aromatic, having non-planar tube-shaped geometry. Let us now examine the behavior of higher aniline in the light of Huckel rule. 10 aniline contain Huckel number of electron n is equal to 2 and thus should be aromatic if planar. But due to several non-bonded interaction between the internal proton, the molecule has a non-planar geometry. Thus, non-planarity of the ring prevent delocalization of pi electron and thus 10 aniline is non-aromatic and give typical addition and oxidation reaction of alkene. 10 aniline 8 pi electron non-planar non-aromatic. 19 methanol 10 aniline 10 pi electron nearly planar aromatic. 910 oxa 10 aniline 10 pi electron nearly planar aromatic. 910 aza 10 aniline 10 pi electron nearly planar aromatic. In contrast, 910 methone 10 aniline second is very nearly planar since the non-bonded interaction between the internal proton are removed by introducing a methylene bridge. As a result, delocalization of pi electron can occur and hence the molecule is aromatic. Likewise, its oxygen third and nitrogen aniline fourth are also aromatic. Besides, these are a number of higher anilines such as 12, 14, 16, 18, 20, 24, 22, and 30 has been prepared and their aromatic and anti-aromatic non-aromatic character investigated. And 12 aniline 12 pi electron anti-aromatic, 14 aniline 4 pi electron aromatic, 18 aniline 8 pi electron aromatic. NMR studies have been shown that 14, 18, 22, 30 aniline which contain 4 and plus 2 pi electrons are aromatic, while 12, 16, 20, 24 aniline which contain 4 and pi electrons are anti-aromatic. Thanks.